Okay, so year 12. Second example of a proof by contradiction. So here we need to prove by contradiction that root 2 is an irrational number. Now this is quite nice because you know already that root 2 is irrational. It just goes on and on and on. And now we can actually use some like mathematical proof to show why this is a true statement. So first of all, we're going to make our assumption, which is like our contradiction of the original statement. So our assumption would be that root 2 is not an irrational number, or root 2 is, I'm just going to switch pen for this, it's a little bit easier, that root 2 is a rational number. That's what I'm assuming. Assume. Okay, now, a rational number is kind of any number that can be written as a fraction, okay, and where both the numerator and the denominators are integers, okay. So if it was rational, then root 2 could be written in the form a over b, okay. And two things would need to be the case here. A and b would be integers. Oh, can't spell. Integers. And a over b is in its simplest form. Okay, and that is, it's like it looks more complicated than it is, but all this is saying is that any rational number can be written as a fraction in its simplest form. Okay, now let's just go back to this then. If we've got root 2 equals a over b, I could square both sides, and when I square both sides I would get 2 equals a squared over b squared, like that. And from that I can get 2b squared equals a squared by multiplying both sides by b squared. So just thinking about what we know for definite at this stage, the left hand side here is even, okay, this bit is even. So since the left hand side is even, the right hand side is the same, so the right hand side has also got to be even, okay, and that means a must be, a squared is even, sorry, and a must be even. Okay, so because a is an even number, we can represent a in the form 2k, where k is an integer. Okay, so a can just be written as 2k. So because of that, if I just rewrite this line of working here, so 2b squared equals, instead of writing a, I can write 2k squared, which therefore gives that 2b squared equals 4k squared. Simplifying that down then, we get b squared equals 2k squared. Now, at this point, the right hand side is definitely even because it's being multiplied by 2. Okay, so since the right hand side is even, b squared, this bit is also even, and b must be even, therefore b is even. And this has led to a contradiction, okay, and the contradiction is this: if a and b are both even, then a over b is not in its simplest form, okay? So if a and b are both even, a over b is not a fraction in its simplest form. Okay, so that's the contradiction. So we've negated our original thing. This is our negation bit. We've shown it leads to a contradiction, and because we've shown it's led to a contradiction, that means we conclude that the original statement must be true. So the original statement up here, proved by contradiction, root 2 is an irrational, must be true. So conclude therefore root 2 is an irrational number. Couple of things about this. I'll just move so you can kind of see all of the proof in one go. It won't be very intuitive at first. Like this whole just multiplying by b and then like the whole squaring both sides and then multiplying by b squared and blah blah blah. It's not very intuitive. A lot of you won't think. A lot of you will look at this and be like, well, I've got no idea what I should even do. With practice, there are certain proofs that use the same sort of structure each time, and that will really help. Useful things to try and do are trying to spot like odd and even bits and then substituting in. That often gets you somewhere. And even if you can't get all of the way there, bits and pieces will help to make it a little bit clearer. So it is super important that even when you're looking at it thinking I've got no idea how I can possibly get to a final conclusion, that you just have a go and try doing some manipulation to see if that helps make the problem a little bit clearer for you. We'll leave that one there and then just do one more example of proof by contradiction. Okay, so year 12, this one here, we've got to prove by contradiction that there are infinitely many prime numbers. Now this proof is kind of like the wordiest one yet. It feels like there's the least kind of actual mathematical manipulation to be doing, but you do just need to be thinking really hard about what's going on. So our first step, our assumption step, we are going to assume the negation. So our assumption is going to be that there are finitely many prime numbers, okay, that they don't go on forever, they stop at some point. So we're going to assume that there is a finite list of prime numbers, okay? So far, so reasonable. Now, from that, if it's true that there is a finite list of prime numbers, we can list out all the prime numbers. So the first prime number, we could call it P1, and the second prime number would be P2, and the third one would be P3, and so on and so on and so on. All the way up. The very last prime number, we'll call P to the end, because we don't know how many there are. We don't need to know. Now, just thinking super, super hard here at this step. If we think about, so if we consider this, if we consider the number n, we say n is our first prime times our second prime times our third prime, all the way up to our final prime number plus 1. So just think about that number there. So this number here is all of the prime numbers multiplied together plus 1. Now, when you divide n by any of the prime numbers, so by any of P1, P2, Pn, the remainder would be 1. Okay, the remainder would be this one just here. And so because of that, this n is not divisible by any of the prime numbers, okay? So therefore, n is not divisible by any of these primes, like that. And what that means then, therefore, either n must be prime, n itself must be prime, n itself must be prime, which makes sense, or It's prime factorisation. So if you did the prime factorisation of our number n, its prime factorisation would contain only primes not on our original list. Let me just write that down and explain that a little bit clearer. Okay, just 1 second. So explain what's happened here then. So in terms of numbers, all rational numbers are either prime numbers or can be written as the product of prime factors. So like by doing your factor tree. So here, with our number n must either be a prime number or its prime factorisation must feature a different list of prime numbers than our original finite list of prime numbers here. Okay, so this is our contradiction. Our contradiction is this. So this contradicts the assumption that our list P1, P2, P3, Pn contains all the prime numbers. Because either n is prime and it doesn't contain n, or there are some other prime numbers that we just didn't include. And so because of that, we can now write our conclusion. So our conclusion, we just restate the thing we were trying to prove. Our conclusion is, therefore, I'll go back up here. Therefore, there are infinitely many prime numbers. Okay? And thus concludes the proof. This is tricky, year 12. Like, I would expect that you will find this hard. It is like a challenging thing to get your head around. Just so you know, the remaining section of this chapter you're not going to find as hard as that. So the stuff on partial fractions will be absolutely fine. The stuff on all of that will be absolutely okay. It's just proof by contradiction, I think, is quite tough. I'm going to have a go at the textbook bit now. I'll write some more notes and stuff. I'll show my homework for you. And we will see how you get on. Good luck.